Hey there, you crazy cats. It's been a while. Glad to have you back. Today we're going to talk about work and power. You're going to learn how to calculate work. You're going to learn how to calculate power, essentially. We're going to do a little bit more than that, but not a whole lot. Work. Work is the magnitude of the displacement times the component of the force parallel to the displacement. Force applied to, and what this really comes down to is force applied to an object for some distance. Work equals what says the product of the displacement, so that's basically the distance for the most part it traveled, as we would say, and then the parallel force. So work equals force times distance. And then right here would be our equation with just the letters. And right here it says the component. That's a key term right there because of the force to the displacement. And what we say that then is to get that component, that is cosine of x or cosine of theta, as long as we're measuring from the x-axis. All right, so the work equals force times distance times the cosine of x. So here's some examples then. It says in A there is a force but no displacement. So in example A, there's no work being done here because there's a force but the distance is 0. So in our equation, force times distance, well, that would be 0. Anything times 0 is 0. In B, force is parallel to displacement. So we have simply would take the amount of force or the tension of the string times the distance that they were to pull the skier. So this is a really simple one, just force times distance. But in C, the force is at an angle to the displacement. So as you can see here, the lawnmower, push mower, is being pushed to the right. So it's going to cover some distance, but she is pushing down. So what we find out here then is that the force, to find this component that is parallel to the distance, all right, we're measuring from the x-axis, so it would be the force times the cosine of theta, or the parallel forces they're saying here is equal to the force times the cosine of theta. And that's what we see here, is that the work is equal to the parallel force times the distance, or F cosine of theta times the distance. Things that we want to talk about, we haven't talked about yet here, is the unit of work. It is a Newton meter. All right, we have forces in newtons, distances in meters, so it'd be Newton meters. And in physics, we typically call a Newton meter is called a joule. So the units typically, because it is energy, would be joules. Joules is the units for all energy. Okay, if there's more than one force acting on an object, it is useful to define the net work. So in this example here, they're showing us a box, and they've got several forces that are acting on it. In this case, we have this kinetic friction that's pulling back. Kinetic friction, which is pulling back on it, it's wanting to travel down. And then we also have the component of its weight that's pulling it forward, and that's what we commonly refer to this mg sine theta right here as the force pulling it down. And then we'd use our sum of forces and find out what then is the net force pulling on it. We could take that times the distance that the box would travel. You're pulling your dog's leash at an angle of 23 degrees from the horizon, trying to get it to come 0.8 meters to you. You're pulling with a force of 100 newtons. How much work have you done? Well, in this case, they've given us an angle. They've tell us that the distance is 0.8 meters, and the force is 100 newtons. So work equals force times distance, and we're using an angle here, so I'm going to go ahead and throw in cosine of theta or cosine of x. The force is work then is equal to 100 times 0.8 times the cosine of 23 degrees. And what we get then for an answer is the work is equal to 73.6 joules in this case. All right, work done by a variable force. In this case, variable force meaning the spring. The amount of force that the spring is going to pull with is going to change depending upon how far it's been stretched. The force of the spring is equal to negative kx. In this case, K represents the strength of the spring, and x represents the distance it has been pulled. So K is the strength, and x is the distance, or the displacement, put a T in there, displacement of the spring. Okay, so we have here a 1,600 kilogram car's front bumper has a spring strength, all right, or an elastic strength, we could say. I mean, however you want to word it. I really don't care. 15,000 newtons per meter. That means if you were to push this bumper in a meter, which would probably be a little bit impossible, but you can get it to move or bend it, is smashed in 3 centimeters in a collision. Find the force created by the bumper. Well, the force of the spring strength, or the bumper strength in this case, is equal to negative kx. In this case, the k is 15,000, and x, 3 centimeters into meters, is 0.03 meters. So the force of the bumper is negative 450 newtons. Now, let's talk about this negative here. We haven't talked about the negative yet. The negative tells us that the force is in the opposite direction that the object was moving, the car was moving. So this bumper would apply a force that was in the opposite direction of whatever hit it. All right. Find the work done by the bumper. Well, work equals force times distance. And I'm going to throw this cosine of theta in here, just to show you in this example here that work is going to be equal to negative 450 times 0.03, and then the cosine of 0. Well, you trig buffs here, and you guys are really good in trig. What is the cosine of 0? The cosine of 0 equals 1. So when we have something that's completely parallel, this equation still works because cosine of 0 becomes 1, and it would just be work equals negative 450 times 0.03 times 1. And a lot of times we won't worry about that. So the work was equal to 13.5 joules. Not a whole lot of work that was done by this bumper. Alright, a few things here for you to do. Talk about in your notes. Make sure you're ready to talk about this tomorrow in class. First of all, what is work? I want you to give an example of work, and something that your example can't be anything that we just talked about in our notes. Give an example where there is force and distance but no work. All right, give an example where there's force and distance but no work was done. That's going to be a tricky one for you. I'm going to give you a hint. Think about that component here, the cosine of theta. When would that mean that there was no work? Can we adjust for force and an angle? Or how can we adjust for force and an angle? Do a little research. I want you to Google this. What is power? All right, is power greater when what decreases? All right. So this is something that we're heading into. All right, work. Power is usually what we talk about after work. So do a little research. Find out. Google what is power. That ought to be easy for you. And then power is greater when what decreases. All right, what's going to have to decrease? It's a concept that we've talked about. Hey, I'll catch you guys on the flip side.